In this video, we're going to focus on a type of sequence called an arithmetic sequence. Now, this is one of the two main styles that we have to look at advanced higher. When it comes to arithmetic sequences, what we have to be able to do is we have to be able to determine the standard form of them, how they look like in general. We have to be able to get set arithmetic sequences and how they look, calculate various terms, and then ultimately calculate, if it has a limit, what that limit is. First thing though is we need to make sure that we know some of the terminology and some of the basics of sequences that we should have covered at the various levels up to this point. So the first thing we need to remember is a sequence is an ordered list where terms are found following a set rule. So there's a rule that determines how each of the terms is calculated, and you have to use that in order to be able to do it. What we also know is that the nth term of a sequence is denoted by un, so written like this. So for example, u1 represents the first term of the sequence, u2 the second term, u100 the 100th term of the sequence. And it's defined by a recurrence relation. So what we do is we define un plus 1, which is the next term in the sequence, as a function of earlier terms. So put in basic terms, this term depends on something that happens to the term before it. Now this helps us to define what's called a first order recurrence relation. Now this means that un plus 1, so our next term, depends only on the previous term, not any terms before that. So we sometimes get terms where we've maybe got un plus 2 equals something happening to un plus 1 plus something happening to un. That is not a first order recurrence relation. It's only first order when the next term depends on something happening to the previous term. And first order recurrence relations take this format here. So un plus 1 equals r un plus d. So something happening to the previous term plus or minus something else. So it's scaling it up or down, and then we do something to the answer after that. Now one key thing to note is that if we know the first few terms of a sequence, we don't have enough information to identify the formula for the sequence. So I couldn't tell you the first three terms of a sequence, and then you can turn around and tell me, oh, un plus 1 equals this. But if we know it is a first order linear recurrence relation, then we can identify the next term in the range of values for r and d. So it just, in general, we can't do it. But if we know it's a linear first order recurrence relation and it's going to take this format we just mentioned, then we can use the terms and the relationships between them to calculate that. Another big thing we are able to use and we're able to say about a sequence or a series of numbers is that if we ever obtain a value for n where the next term is equal to the previous term, which is equal to some value k, then k is called a fixed point. Now you can think of that as a limit to the sequence, i.e. it's never going to go above that. Think of it in terms of limits of functions when we looked at that. It's what a point tends to in terms of the overall value. Now if we look at the general format for a linear recurrence relation, if the values of un, so this recurrence relation here, if they move towards that value of k, then the fixed point is stable. So let's imagine I was drawing this as a graph and I had my sequence and the values of the sequence tended towards the k like that. This fixed point is called stable, i.e. the points are all going to go towards it. It's going to be essentially a limit for the function, the highest value we can get. Now this all depends upon a part of this series and a part of the formula, which is this, the r in front of the un. If the size of r is less than 1, we are able to say that the fixed point of the series is stable. So it's never going to go above that. However, if it's moving away from that fixed point, so imagine we had a sequence and it did this, the fixed point is then unstable. And again, we can look at the recurrence relation and determine whether it's stable or unstable by looking at this value of r. If the size of that value is bigger than 1, what's going to happen is every time we multiply, it's going to get bigger and bigger and bigger, so it's going to be an unstable point. We're never going to get a limit when it comes to that. Now that's a lot of information to take in. Key things we have to make sure we remember is what a sequence is, linear first order recurrence relations, how they look and what format they take, and this part here about stable and unstable points. These are all the key vital bits of information that we have to be able to use and work with at this level. Now let's imagine we have an arithmetic sequence. If we ever get a sequence where un plus 2 take away un plus 1, so the second term take away the first term, is the same as the un plus 1 take away un, so that first term take away the previous term, they're always equal to some value d, we are able to say that these form an arithmetic sequence. So we could, for example, have a sequence that goes 1, 4, 7. If I was to do 7 take away 4, I would get 3. If I was to do 4 take away 1, I would get 3. So these values here would create an arithmetic sequence. Now this d, which if we were to look at this example again was 3, this is called the common difference. So what that means is essentially it goes up by that amount every time. And traditionally this means that we can write our linear recurrence relation in this format here, where un plus 1 equals un plus d. So the next term equals previous term plus this common difference. And what we always say is that u1, our first term, is equal to some value a. So in this case, u1 would be equal to 1, so a would be this value 1. It's where we start the sequence and where we then build upon and build up. Now what we're able to do is use this fact to come up with the general format for terms in an arithmetic sequence. The nth term in an arithmetic sequence can be given by this formula here. So un equals a plus bracket n minus 1 times d. So a here, that's our starting point. So that's our u1. The d here, that's our common difference. And n minus 1, well, that's the previous number for n. So if I had u2, I would have 2 take away 1. So it would just be the first term, add on one of the common differences. Now this can be proven in a variety of manners, but the key way to prove it is using proof by induction. Now you can imagine, as we said before, this would give me the fact that u1 equals a, u2 is equal to this a plus d, u3 is equal to a plus 2d, and so on like that. That's how the terms for this sequence would look. Now this pattern here suggests it would look like that. So I've got a plus 2 for this, well n is 3, so 2 is the n minus 1 there. So what we can do is have a look at this. Now imagine I took u1. If I was to look at u1, that would be the equivalent of a plus 1 minus 1 times d. 1 minus 1 is 0, so that would be a. So that would be what our starting point is. So we know it works for the initial point. Let's imagine then, because it looks like it takes the format we want, that any term un equals a plus n minus 1d, it works for that. So it's valid for that. If we can now prove it works for the next term, we know this is how the nth term can be given. So let's imagine then, I want to look at the next term, un plus 1. Well, I know un plus 1 is going to be equal to my un plus this common difference d. So it's going to be equal to the previous term plus whatever the d is. Now I know my previous term is given by a plus n minus 1 times d. It's then going to be plus another d here. If I multiply this bracket out here, I've got a plus nd, take away d plus a d. This minus d and d cancel, which is a plus nd. So I can say then that my un plus 1 equals a plus nd, which is given by the format here. The only difference is my n here would be n plus 1, which here would give me n plus 1, take away 1, which would leave me with nd. So there you go, it works for the next term. So they would say, right, it works for the first term, works for a generic term, un, works for the next term, un plus 1, so we know that it's true. So it's going to be true for every single value that we want. We know then the nth term is given by this formula here. un equals a, the start term, plus n minus 1 d. And we have to bear that in mind because we have to be able to use that when we're working with it. Let me show you the kind of things that we have to be able to do with it. Let's imagine that I give you an arithmetic sequence that goes 6, 11, 16, and it will then continue on. I want to find the nth term, So that means find some sort of formula for un. And then I want to find the 10th term of the arithmetic sequence. So let's start by looking for the nth term un. Well, remember, we said that un equals a plus n minus 1 times d. Well, from this, we know that u1 is equal to the a, which is our first term, which in this case is 6. We then want to find out the common difference d. Well, I know that u1 is 6, u2 is 11, and u3 is 16. If I was to do u3 take away u2, I'd get 5. If I was to do u2 take away u1, I'd also get 5 there. So what I can then say is that d is equal to 5. So for this sequence here, I'm able to then say, right, I can get the nth term by doing un equals 6 plus n minus 1 times 5. Now that looks like a great bit of fun there, but I want to write this as simply as I can. So what I'm going to do is multiply out the bracket here and simplify everything as much as possible. So I know then that's going to be 6 plus 5n take away 5. So my nth term is going to be given by 1 plus 5 times n. That there is the formula for the nth term of my sequence. Second one, I want the 10th term, so in this case, I know that n is equal to 10. So just put that into the formula. What I'm able to say then is fine. I know that u10 equals 1 plus 5 times 10. 5 times 50 plus 1 is 51. So there you go, that's the 10th term of your sequence. If you were to continue to work on to get there, you'd eventually find that that's where you go. So we can use it in this manner for finding formula for nth term and then calculating terms beyond that. But we're also able to determine arithmetic sequences if we know several of the terms and their position within it. So let's imagine I tell you that I've got an arithmetic sequence where u3 is equal to 9 and u7 is equal to 17, and I want to find the format of this arithmetic sequence. So looking at that, you could probably say to yourself, well, I can look at what's going up and figure out numbers of places and see from there, but we have to use our general format for it. Now, we know for an arithmetic sequence that we're able to say the nth term, un, is equal to a plus our n minus 1 d. Now, in this, for an arithmetic sequence, we need two things. We need the a and we need the d. So we've got two unknowns. Well, I've got two bits of information here, so I can determine two systems of equations linking a and d, and then solve them using simultaneous equations, which we've covered in previous years. So if I use u3, what I know is that u3, which is equal to 9, gives me that 9 equals a plus the n minus 1. Well, I know that the n is 3, plus 3 minus 1 times d. So from that, I know that 9 is equal to a plus 2d. I can then use the u7 to tell me that, right, 17 is equal to a plus the n minus 1. Well, in this case, I know that the n is equal to 7, so 7 take away 1d. So what I can then say is I know that 17 is equal to a plus 6d. So from that, I've got two equations linking a and d. I can solve them simultaneously and determine the values for a and d. So let's put them together. So I know that 9 equals a plus 2d, and solve them. Treat it like a column sum, take them away. 17 take away 9 gives me 8. I've got a take away a, which is nothing. 6d take away 2d, which gives me 4d. So a equals 4d. I know that d is equal to 2. And if I take that and I substitute it back into one of these two, I can determine the value for a. So let's look at this. I've got 9 equals a plus 2 times 2. So a plus 4 is 9. A is equal to 5. So I've got my a and my d. I can find the arithmetic sequence for that one. And what I can then say is, therefore, un is equal to a, 5, plus n minus 1 times d, which is 2. Multiply it out and simplify it down. I've got 5 plus 2n minus 2. So for this one, I know that un is equal to 3 plus 2n. There you go. There's your arithmetic sequence for that. So we have to be able to use it in several ways like this. You know, determining sequences, determining terms, but the key thing is it all relies on and lies about this general format here. Bear that in mind.